Everybody, welcome back. After those two introductory lectures, today I would like to introduce you to some of the mathematical underpinnings of cryptography. So the topics that we're going to talk about is modular arithmetic. We're going to talk about groups and rings, and then we will revisit two historical ciphers, considering the new tools that we have under our belt. So let's get to the first topic, modular arithmetic. So what you will see in a little bit is that computations in modern cryptography are pretty much always done in finite sets. So these sets may be huge. They may have a number of elements that is some prime with 800 decimal digits, but nonetheless, those sets are finite. And what we're going to do today is to talk about computations in such sets and how to look at these kinds of sets from a more abstract point of view, which is, talking about groups and rings. So a very prominent, well-known example of a finite set is the clock that we are all used to. So let's say I tell you that, 5 o'clock in the morning, that we are going to meet in 10 hours. Normally in English-speaking countries, at least here in the US, you would not say that that we are going to meet at 15 o'clock. Only military people would do that. So what we do instead, we count from 5 upwards, and if we have reached 12, we kind of start. We reset our counting and start, counting again. And that way we actually arrive at 3 o'clock in the afternoon. So if you're familiar, and you all should, you know what the modulo operation means in computer science. So what we basically do here is we say, okay, 5 plus 10. So 5 plus 10 modulo 12 yields 3. So what you see from that is the modulo operation tells us that we are not really interested in how many times the 12 goes into 15. What we are really interested in is the remainder of that division. And this idea is the basis of a new concept that we are going to use a lot, which is congruence. And I have already used, the operator for congruence here, which looks like an equal sign. It's just one dash more. So let's look into the formal definition of congruence. So let's assume we have an integer a, and we have a remainder r, and we have a modulus, all of which are integers. And the additional requirement that we have is that our modulus is bigger than zero. So it's a positive integer that cannot be 0. Obviously, because we can't really divide by 0, as you know. So what you know so far using the modulo operation is we can write a modulo m is r, and that's how we say it. A modulo m is r. So with the new operand here, what we say is A is congruent modulo M. A congruent modulo M. Okay? So what does that mean? What exactly does it mean? So we made a connection from our, modulo operation to congruence, but let's give a more formal and direct definition of what congruence actually means. So here it is. A congruent R modulo M is exactly the case if M divides A minus R. So the way how we read that dash here is divides, okay? It's another operator. So M divides A minus R. So think about it for a second. What's happening here? Remember that originally we were dividing A by M, and that yield a certain remainder. Now, when you think about it, you subtract that remainder from R, the result actually should be divisible by M. And this is how congruence is actually defined. And this has very certain, very important implications that we are going to look into in a second. So again, we subtract the remainder of from A, and what we receive is necessarily something that can be divided by M. Okay, so quick example here, A being 20, the modulus is 9. So what we can write is that 20 equals 2 times 9 plus 2. So the remainder here is 2. And what you should convince yourself is we chose this 2 here just big enough so that our remainder would be the smallest possible positive remainder, 2. So in other words, that said, we can write 20 is congruent to modulo 9. Sorry. Okay. So 20 congruent to modulo 9. And this is because 9 divides 20 minus 2. Okay. So let's look at the somewhat interesting implication of when you define the congruence as we did by M divides A minus R. So a different way of writing that is A is equal to a quotient times M plus R. So M goes a certain number of times into A, and what remains is the remainder, of course. So let's apply that thought of the quotient that we actually do not need, but let's consider it for a second. What happens if we play around with that quotient here? Okay, so we said before, that's what we have been covering, 20 equals 2 times 9 plus 2. So the quotient is 2, and please note that the quotient is just about big enough to make the remainder the smallest possible positive remainder that we could get. But playing around with the quotient, we will see that we are going to get different remainders, which are not the smallest positive remainder anymore, the smallest possible positive remainder anymore. So for instance, we could choose a quotient of 1, in which case the remainder is 11. Or we could choose a quotient of 3, which in this case makes the remainder -7. So why are these still valid congruence relationships? Well, because here in this example, 9 divides 20 minus 11. Or in the last example, 9 divides 20 minus 7. So what you see here is that the remainder is not unique. We get different remainders, and we still have a congruence relationship. So 20 is congruent to 2, obviously. 20 is congruent to 7. 20 is congruent to 11. 20 is congruent to -7. And whatever the choice for Q is, we get different remainders. So the remainder R is not unique. So this is one of the biggest conclusions that comes directly out of the way how we define congruence. So any R is congruent, you know, A is congruent to any R where this relationship here is fulfilled, okay? And that's kind of surprising. So in other words, our remainder is not unique, which means our A may be congruent to a lot of numbers. And if our set of numbers is infinite, it's congruent to an infinite set of numbers. So, and this is actually how equivalence classes are defined. So let's look at an example. So let's assume that A is 10 and our modulus is 4. So what we get here is, you know, 10 will be congruent to 2. Of course, that's the smallest positive integer because 4 divides 10 minus 2. But our A is also congruent to 6, to 10, to 14. It's even congruent to -2 for the very same reason, because our condition holds. And we can always say, even here for the -2, we can say 4 divides 10 minus -2. So all of these numbers that A is congruent to, they form what we call an equivalency class. So you see the equivalency class here, the elements that make up the equivalency class. All are equivalent with respect to modulo 4. So we see the original 2, and then we get upwards here because each of the elements have a distance of the modulus, which is 4. And the same is true for if we go backwards. So all of these elements form in an equivalency class. And we are going to see in a minute why these elements are being considered equivalent. So for now, let's just state that all members behave equivalent modulo 4. All members of a equivalency class. So obviously, we can have different equivalency classes depending on the choice of A. So instead of an original remainder of 2, what we had so far, we may have a remainder of 3. Like for instance, if we choose A to be 11 instead of 10, okay? So that would change our equivalency class, and we get a new equivalency class where again the members have a distance of 4 in both directions. Okay. So the question is, how many equivalency classes can we have considering modulo 4? Well, if we do modulo 4 operations, we can only really have 4 different kinds of remainders. The remainder, you know, the smallest positive remainder could either be 0, or it could be 1, it could be 2, as we looked into already, and it could be 3. And then we go over again to 4, which is the same as 0. So let me remove that. Okay. So here you see all 4 equivalency classes. Okay. And we indicate with dots that the number of elements stretches to infinity, to the left and to the right, into negativity and into, you know, infinitely positive numbers. So now comes the real surprising thing. What we said is all members behave equivalently concerning modulo 4. So how can we actually make use of that idea, and what does it even mean to begin with? So let's just assume that we want to do some sort of computations that are very common in modern cryptography. So let's assume that we want to compute 16 times 15 minus 14 congruent what modulo 4. So we want to find whatever the question mark here is a placeholder of. So of course, what we could do is we could, you know, come up with the result of 16 times 15 and subtract 14, and then do the modulo 4 and see what the remainder is. But in reality, that may be pretty impractical, or at least really painful, because these numbers may be incredibly large. And when we mean large in cryptography, it may be on the order of hundreds of digits, decimal digits. So what we can do, however, we can, before we compute this product here, for instance, and arrive at a relatively large number, what we can do is we can replace these numbers here with their equivalent, with equivalent members of their corresponding class. So I gave two versions here to just make the point that we always arrive at the same result. So 16 obviously is too big for us. What we can do is instead we can choose 4. Because, why do we choose 4? Because it's in the same equivalency class. Actually, we may choose 0, which is really cool, because then you know, the product turns out to be 0. But anyways, let's just do that thought experiment. And 15 we, replace with 7. So 4 times 7 is 28, minus 2 is 26. And this is congruent too, because we have the 24, 26 is just, 2 bigger than 24, and 24 is divisible by 4, so it's 2. So in other words, that 2 is the result for this original, expression. So similarly, we may have chosen different numbers here. Instead of the 16, we may have chosen, 16 here, we may have chosen 8. And instead of 15, we may have chosen -1. And instead of 14, we may have chosen -2. And it would still yield the same result. So 8 times -1 is -8, plus 2 is -6, which obviously is congruent to modulo 4. So the really cool thing is that we can replace any number with a member of its equivalency class in such operations. So one convention that we want to apply, and one word of warning, sometimes I will require you for convenience and by convention that we pick actually the smallest positive member of a class. So by convention, because we don't want to just go with any number, so by convention, I want you to pick, and I will make it clear in assignments and stuff when I want you to do that, that we pick the smallest positive remainder. Okay. So in a broader scheme, to expand upon what we just said here, computing the result of expressions like that, or I should always include the modulo. So in cryptography, what you will see is numbers that we need to compute that are the result of a certain base to an exponent. So those exponents may be huge, okay? So here in this simple example, what we can do is, or as an example, we just say that we want to compute 3 to the power of 6. And what would the result be, modulo 4? What would it be congruent to? So, well, what we can do is we can apply what otherwise we call modulo reduction. So we try to shoot for making those numbers real small. And you can see already that, 3 to the 6 is not exactly easy to compute in your head. And if you imagine that these numbers are huge, and we will, by the way, come up with efficient algorithms that help us to compute, expressions like that. So remember that 3 to the 6 is 3 to the 3 times 3 to the 3. And that's better, easier to compute. So we see that 3 to the 3 is 3 times 3 is 9, times 3, is 27. So 27 modulo 4 would be 3. 27, 24 plus 3 is 27. So 24 is divisible by 4. So we have the first expression yields a 3, the second expression, 3 to the 3 yields 3, 3 times 3 is 9, modulo 4 is 1, okay? One other thing that we could do is just say, okay, 3 to the 6 is 3 to the 2, and that to the 3. So 3 times 3 to the 2 times 3 to the 2 times 3 to the 2. And we already said that 9 is congruent to 1. And we also see that in the equivalency class up here. So we have it here, 9. An equivalent member is 1. So we can say here that, 3 to the 2 is 1. And it's 1 times 1 times 1 is 1, which obviously is congruent 1. Okay. So what you should have learned is to understand what congruence is and understand what equivalency classes are, how many equivalency classes we have given a certain modulus, and how to use the equivalency relationship in order to simplify computations that we do, with the modulus operation. Okay, so now comes a little bit of a break and a step into very, very abstract territory. And we are going to talk about groups first, and then about integer rings. So first off, I want you to be exposed to these concepts already early on, so that you have quite some time to just let it sit. Although we are not going to necessarily use it immediately right away. And the reason why we are talking about groups here and then about integer rings is that, remember what I said in the beginning, in cryptography, we are doing computations in finite sets. So in order to complete the picture, we need to talk about the question, what are finite sets? For our purposes here in cryptography, what are finite sets? And this is exactly why we talk about groups first, and then based on that about rings. And it's like being thrown before a bus a little bit. It's gonna be very abstract, very, very quickly. And later on in future modules, you will see how this all makes sense. So let's talk about groups first, and then we talk about rings. So what are groups for our purposes? Groups are abstract structures in abstract algebra. They are two things: a set of elements with a group operation. So these two things we are going to look into: a set of elements, and you apply an operation here that you see as a donut, okay? So in other words, that donut here is a placeholder for concrete operations, and the concrete operations that we will put here are addition and multiplication. And by way of doing that, we are also going to cover subtraction and not quite division yet here. But what you see is that we really only need multiplication, addition in order to also cover subtraction and division, because it's basically just operation with inverses. And what that means, we're going to talk about in a second. So what are the important properties of groups? So first off, when we apply the group operation to two elements in the group, what we expect to happen is that the result is also going to be in the group. So we call this closeness, okay? The group is closed because it would be kind of awkward if we apply our group operation to two elements and out of a sudden the result would be outside of the group. So groups are always closed. This is a very, very fundamental requirement. So let's just consider for now as an example, you know, the realm of integers. And the group operation, let's say, is plus, okay? So when we add two integers, the result is again an integer, and it's also part of the integers of z. By the way, the symbol z comes from the German word Zahlen, which means numbers. So that z that you're well familiar with is actually derived from the German word Zahlen. Okay, another requirement is associativity. So our group operation is associative, which means that if we have three elements like here, and we apply the group operation to these elements, we obviously have a choice. We can first associate B with C by way of the group operation, and then associate A and the result of A plus B. And that would be the same as, you know, if we were to associate A and B first and then add C. So convince yourself that is easily fulfilled for the integers under addition. So now it's getting a little bit more interesting. Let's talk about identity. A group needs to have an identity element. So the one that you see here is really just a placeholder. It does not need to be one numerically. So in our case for the integers, the identity element is actually 0. So 0 plus an element A is equal to that element A plus 0, which is A. So basically that identity element applied to any element results in the very same element. That's the reason why we call this property identity, okay? So let's take a mental note of that 0 that we just defined here in our example to be the identity element for the integers under addition. So another requirement, and that's the last one actually, that is actually required, is that we can invert an element. So we have an inverse of an element. Each element has a unique inverse. So, which means that if we apply the group operation to an element and its inverse, we get the identity element. So there is some, reference to the identity element. So let's just say what, you know, for our example, what the inverse of a number is. Well, it's the same number multiplied by 1, by by -1. So if we have an element A plus its inverse is actually A plus minus A, which you could, should convince yourself it's the same like minus A plus A, which is 0. So remember the 1 here is really just a placeholder for the identity element. And for our example, the identity element is 0. So if groups also are commutative, so if we basically can switch the elements around the group operation and both versions are still the same, then we call this group an abelian group. Abelian from a mathematician who was able. So an abelian group, abelian group. All right. So it turns out that groups are the more foundational structure in abstract algebra. And based on groups, we can now define what rings are. So rings and groups are incredibly important for us, as we will see. And again, what we try to do is here, and I said that already, we act on finite sets, and finite sets have operations operated on them, which are modular arithmetic operations. And for this reason, we look into rings to more formalize the idea of finite sets and modular arithmetic. So what is an integer ring? An integer ring is actually a finite set of elements. So it consists of a set Zn. So remember, instead of the general infinite group of integers, the Zahlen Z, we now have a footnote here, which is M. And M actually tells us how many elements we are going to have in our set. So we start at 0 and have all the elements up to m-1. And all of them are positive integers, including 0. So we have two operations, which is the plus operation and the times operation. And how are they defined? Well, it turns out they are defined exactly as our plus and times operation, except that we apply modulo m. So we have a modulus, and the modulus coincidentally is the m that we have as a footnote here. So a plus 1 is congruent C modulo m. That's how the plus operation is defined. And a times b is congruent D modulo m. This is how the times operation is defined. So what are the properties of integer rings? So we now know what integer rings basically are, what the set of elements are, and what the operations on these elements are. Let's look now what the properties of those integer rings are. Well, it turns out that integer rings are groups under addition. So the group operation that we define to be donut above is plus modulo m, and the neutral element is 0. Okay, so neutral element is 0. Pretty much like the example that we talked about before, over the realm of integers, except that our group here is a finite group. It's a group of elements which is a finite set. So, and the idea of subtraction is the application of the inverse. So we know that we have of any element of this finite group, we can get the inverse by just prepending a minus sign before that element. And that way we get the inverse. And if we apply this inverse to an element, plus modulo m, we get 0. Okay, so in other words, the idea of the inverse here helps us to actually implement subtraction. So subtraction is just the addition of an element and an inverse of another element. So, and the whole thing modulo m, okay? So our rings, and we have a second operation. So we have the times operation, and rather the times, modulo m. Does that operation work? Obviously, the multiplication works. But I said rings are almost groups under multiplication. So why is that? The reason is that invertibility is violated. So we don't really have a group under multiplication. And this is because one of these conditions, remember, not every element in this ring has an inverse under multiplication. So you can check that for yourself. So the inverse doesn't always exist, okay? So what you will find is, and what I would like to just state here without proving it, an inverse exists for all elements that are prime, relative prime to m. So let's say we have m is e.g. m is 6. So numbers that are relative prime to it, the only number here is really 5. So why is that? Because 6 is 2 times 3. So the greatest common divisor, that is what we needs to be 1 for any element that has an inverse. So obviously, when we look through the elements from 0 up to 5, the only element that has a greatest common divisor of 1 is 5. So because 2 doesn't work because we have a factor of 2 here, the prime factor. 3 doesn't work, we have a prime number 3 here. 4 doesn't work because, again, we have the 2 here. So they're not relatively prime. It turns out 5 is the only number that is relative prime to 6, okay? So that is the reason why, the reason why we have not a group under multiplication is because the inverse doesn't always exist. So a sufficient condition that needs to be fulfilled for an inverse to exist is if the element that we look for having an inverse is relatively prime to the modulus. So in other words, if the modulus is a prime number itself, then every element in the group has an inverse. So I say it again because it's so important. The condition for an inverse to exist for an element is that the element is relatively prime to the modulus. So here A needs to be relatively prime to M. If M is a prime itself, so if we choose the ring such that M is a prime, then every element of the group has an inverse. So here, right here, you see the rationale why we are pretty much always, when we define groups, pretty much always will see that the order of the group is a prime, so that our modulus M is prime. Okay, so this was our little exploration of rings. So let's tackle the last chapter, which are historical ciphers. And it turns out with the modulo operation, it's much easier now to actually, come up with the encryption and the decryption ciphers for some of the historical ciphers. And as examples here, we use Caesar's cipher, and we use the affine cipher, which we have not talked about in the historical ciphers, but let's go one by one. So as you know, Caesar's cipher is a shift cipher, and in the old days, Caesar only shifted always by 3 letters. We may generalize this idea and say, okay, let's shift any number of keys and the key, any number of letters. And the key is, the secret key, if you want, is the number of shifts. So convince yourself that we have a key space of 26. Realistically, actually 25, because the identity shift is not very interesting because it doesn't encrypt anything. So with the ideas that we developed above, it's really easy to express our encryption and decryption ciphers. So the encryption cipher for a letter X is just, congruent to X plus K plus the key, X plus the number of shifts, modulo 26. So convince yourself that the modulo is important in order to elegantly manage the wraparound. Let's say we want to shift the letter Z by 5 positions. Obviously, that results in a wraparound, and we start at the beginning of the alphabet again. So this is an interesting way how to express that elegantly and mathematically correct. So the decryption is just the inverse of that. So what we do is, if this yields Y, what we need to do is we need to subtract K from Y modulo 26. And this would yield the original, X. Okay, so We talked about attacks already. So brute force would be one. Why is brute force an option? Remember that the key space is ridiculously small. So we have 26 cases to check. So brute force is a very viable attack method here. And the other one is frequency analysis. So the frequencies of the letters are not really changed. So the same letter is always going to be encrypted with the same cipher letter. So we can apply frequency analysis. So let's talk about a different cipher. Looking at the Caesar cipher, we may under the impression that we kind of complicate it somewhat more if we kind of complicate this term here and this term, okay? So the idea here is that we come up with a key that has two parts, a part A and a part B. So and instead of doing a shift right away as we did before, what we would do is we would multiply, and this multiplication is the kind of multiplication that we saw in the integer ring. So we multiply x with a, and then we shift, okay? And we do the whole thing modulo 26. So really y is congruent to a times x plus b mod 26. And again, it gotta be 26 because we are dealing with 26 letters. If we have a different alphabet with a different number of letters, then we would need to, put that number here. Okay, so how do we find, given a cipher letter y, how do we get back to the plain text letter? Well, what we do is, and convince yourself that we just do the opposite operation. So given this, we subtract b and we apply the inverse of a, okay? So that yields this formula for retrieving the plain text back. So now comes already in handy what we talked about above with the integer rings. So we can only choose an A that actually has an inverse. So it works only if the greatest, let me see, that's an error here. The greatest common divisor of A and 26 is 1. So that's a condition. A must be relative prime to 26. And 26 is not a prime, so we cannot expect that any element, smaller than 26 would work. So, well, what does work then? Remember that 26 is 2 times 13, okay? So which means that A cannot be divisible by 2, and it cannot be divisible by 13. Otherwise, it would not be relative prime to 26. So, which means that A cannot be even. And from all the numbers that we that we get, it cannot be 13 either. So which means that from 26 letters, we discount all the even numbers, and then we also discount 13. So discounting from 26 all the even numbers, that would be 13 numbers that remain, all the odd numbers, of course, and then we discount 13. So our space for A is really just 12. Okay. So now, what are viable values for B? Well, for B, all viable numbers could be, between 1 and 26. Why is that? Because we have mod 26 here, and after that we wrap around again. So it does make sense to say that B would be 100, 500,000 or whatever. So the space that makes sense really for B is 26 because of the wraparound of the modular operation. So 26 times 12 is 312. This is really the key space that we have. So it's better than 26, or 25 compared to the Caesar cipher above here. But it's still ridiculously small given today's capabilities of computers. So in other words, the brute force attack is still a viable way to attack the cipher. And when you think about it, and you look at the way how encryption and decryption is being done, we still have the situation that a certain letter is going to be fixed, mapped to another cipher letter, and that mapping is fixed. So in other words, the frequencies of the letters do not really change. So in other words, the frequency analysis is still, again, a viable attack here for the affine cipher. Okay. All right. What you see here is that our knowledge about integer rings have already helped in discussing the affine ciphers. Okay. All right. That's all for today, you guys. And I see you in the next class. Thank you.